Max Levy said, I bet you could model Huygens' pendulum with that software. And I said, well, maybe if I knew what it was. And he explained that Huygens had invented a pendulum whose period was independent of the amplitude. He did that by wrapping it round an inverted cycloid curve. So I modeled it, and he said, wow, that's great, my dad would love that. He's written a couple of books on that sort of thing. And that's how I got my autographed copy of The Mathematical Mechanic by Mark Levy, a book that administers a pinprick to the notion that mathematics is the servant of physics. In this book, physics is the servant of mathematics. For example, Fermat, of last theorem fame, asked Torricelli, the inventor of the barometer, given a triangle, at what point would minimize the sum of the distances to the three vertices? Well, Levy's approach to this would be to go to his neighbour's house and bore 3 holes in the table at the vertices of the triangle. He'd then thread strings through these 3 holes, tie them together in a knot, and underneath the table he would attach 3 equal masses to the strings. When he let that system go, the masses would settle as low as possible, and so there would be as much string underneath the table as possible, and so there'd be as little string on top of the table as possible. And so the knot would find the Fermat point. But where would that be? Well, the force in each string is going to be the same, because it's caused by the same mass, and the forces at equilibrium are going to have to balance. They're going to have to add up in a vector sense to 0. The only way 3 equal forces can add up to 0 is if they're aligned along the sides of an equilateral triangle at 60 degrees internally or 120 degrees externally. And so the Fermat point is the point which subtends 120 degrees to each side of the triangle. That point can be constructed geometrically in a number of different ways. Well, the book is full of these kind of little mathematical puzzles. Levy grew up in the Soviet Union, and he said the joke there was that if the West wanted to really put the dampers on Soviet weapons research, they would fly over the research institutes and drop leaflets containing mathematical puzzles. Work would indeed grind to a halt. He also quips that the same kind of puzzles are now used by Russians in Microsoft and Google as interview questions. In either case, the KGB would say that they were capitalist tools. But I wanted to see if his methods could be applied to a problem that wasn't in the book, something else. And a problem came up to my attention a couple of years ago to find the largest equilateral triangle you could draw through the vertices of a given triangle. And I thought, well, I could make a machine for that. So I invented the idea of an equilateral triangle with spring-loaded telescoping sides. And each telescoping side I would fit into a frictionless sleeve which was hinged at the original triangle. And the frictionless sleeves were going to exert a force perpendicular to the sides of the equilateral triangle. When it reached equilibrium and settled, these perpendiculars would have to go through a common point, because at equilibrium, not only do the forces have to balance, but the torques have to add up to 0, or else the thing would rotate. And so these perpendiculars pass through a common point. Because the angles of my equilateral triangle are 60 degrees, the perpendiculars are at 60 degrees to each other, or viewed a different way at 120 degrees to each other. And so that common point is exactly the Fermat point. And so I had invented, I guess, another machine for finding the Fermat point. Well, I mentioned this to a Russian researcher at Microsoft, and he said, well, that's kind of interesting, because converting mathematical problems into energy minimizations, albeit quantum mechanical minimizations, is the core of quantum computing. Thank you.